Thanksgiving.
Today we will be covering our IREC 2025 solutions solving air brakes, which is the story of how the IREC team solved the air brakes problem and reached a target altitude with 0.45% error.
Hi, my name is Quentin. I'm an ME robotics major. I'm level 3 certified in high power rocketry, so I have a lot of rocketry experience. I was the controls sub-team lead last year for IREC, so I oversaw the control system, and a lot of my experience in the past has to do with active control systems, specifically with rocketry.
And if you don't know me, my name is Calvin. I'm a student here at Embry-Riddle studying cyber intelligence and security. I have a pretty extensive programming background, programming for different projects, mainly ones that Quentin over here has roped me into. For this project, I wrote the flight software that controlled the flight. I have past experience with active control, and for this next season, I am the 2026 team lead.
All right, so what is the IREC competition? So IREC stands for International Rocket Engineering Competition, and it's where a bunch of colleges all over the world come together to try and solve a common goal and compete and see who wins. So there's a few altitude categories, so you can compete in 10K, 30K, or 45K. So the altitude is like what your target is. So the goal is to reach a target altitude without going over or under it. So in this case, if you pick any of these target altitudes, that's what you're going to be shooting for. You can also there's also 2-stage categories for 30K and 45K. I don't remember if there's one for 10K or not. But in addition to all the altitude targets, there's also propulsion categories. So you can compete in solids, hybrids, liquids, and also SRAD. So SRAD stands for Student Researched and Developed. So you can do a experimental, like, custom motor of any of those propulsion types in addition to the commercial ones. And the goal is to reach the target altitude without going over or under. So you get a higher score if you're closer to it in either direction. So
We decided to compete in the 10K COTS category. Some of the things that you're scored on are design and build quality of your final rocket, documentation and reports. There's multiple status updates, and there's one final technical report that's due. And then also on flight performance, that's the actual like altitude score, how far you are away from your target. And then there are some bonuses in there for payload, which we'll talk about a little bit later. And in addition to this, there's also the Behrman Award, which is a separate award that's still at IREC. And it is awarded to the team who reaches an altitude closest to their expected altitude. So before you fly, you say, we think we're going to go to 9,800 feet, and then the difference between your actual flight performance and that score is used to determine the Behrman Award. We scored pretty well on this, and we'll talk about that in a minute.
all right, so in 2024, Embry-Riddle Prescott competed in IREC. It used to be called the Spaceport America Cup, but it's no longer at Spaceport America. And they used passive control. So it's just like a regular high power rocket. It goes up, you change the weight of the rocket to try and reach the target altitude, and you really focus on making sure your simulation is high quality to see how close you can get to the target. They were competing in the 10K COTS category. They reached 9,600 feet about, and their target was like 10,500 for the Behrman Award, and they were in the 10K category. So their missed distance was about 900 feet, which is an error percentage of 8.6%. Some disadvantages of doing the competition this way is that it's pretty unreliable. So like if you have bad weather, your rocket's not going to perform the same way that it does in the simulation. Or if your motor like overperforms or underperforms, there's all sorts of variables that you can't control that will affect how close you actually get to your target altitude.
Can I interject one thing? One of the things about solids, the temperature of the grain itself really is highly dependent. The performance of that rocket is highly dependent on that too.
Yep, all sorts of variables with it. Some advantages though is that it's way simpler. So there's not a whole lot of failure points, and a lot of people, especially people that are new to rocketry, like teams that don't have a whole lot of experience, that doesn't really apply to us. It's really good for those teams because they can kind of get into high power rocketry that way.
For the 2025 competition, we decided to use an active control system. We were still targeting that 10,000 feet goal, and we were still using a commercial off-the-shelf motor. Our flight performance, though, was significantly better over the 2024 season. We reached an altitude of 9,756 feet, and we were targeting 9,800 feet. So that's a very significant improvement. We were only 44 feet off of our goal, and the error for that is about 0.45%. Some of the disadvantages to this is obviously adding an active control system. There's a computer on the rocket That adds a lot of complexity. There's also more failure points. If any of those things fail, then the whole flight can be a failure. But some of the advantages, it's so much more adaptable. It can adapt to changes in weather as you go up in the atmosphere, and also your motor performance. And in addition to that, it's repeatable. After the system is tuned, it should be able to fly to the same performance level basically every single time. And on the side, we have a picture of Brick Check rocket, which is this year's rocket.
All right, so this is an image of this year's IREC rocket, the 2025 IREC rocket. It's in a program called Open Rocket. How many people here are familiar with Open Rocket? Okay, great. So most of you. It's what you use to simulate high-power rockets. I'll talk about it a little bit later. We broke the rocket up into a bunch of subsystems. So I'm just going to kind of go over what the subsystems are. The first one is payload. So this is to compete in the payload competition. The payload was located inside of the nose cone this year. The next one is recovery. So recovery located right underneath the payload. That's where you have your recovery electronics, your drogue parachute, main parachute, and making sure that you get the rocket back in one piece. Structures, it's kind of everywhere because it's the structure. And so that's just the airframe, the fins, all the couplers, all of that stuff is handled by the structures team. And then the control system, it's this thing. It's located right above the motor. That's so that when the air brakes open, it doesn't affect the rocket stability as much as if it was further forward. And then, yeah, the last one is propulsion. So that's the motor. In this case, it's a commercial motor. We did initially try to make a SRAD motor, but we had a mishap, so it didn't end up happening at the competition.
For our payload section, we had a live video downlink system set up. It uses an FPV drone camera to capture footage and then a series of antennas to beam it back down to us on the ground. This is an improvement from our 2025 setup. We're using better cameras, better antennas, stuff like that. Some of the challenges for this system are maintaining connection. The camera is very small, that is the entire thing, and it has no onboard storage. So if we lose connection, we just kind of lost that footage. Also, the camera can overheat and obviously shut down, and that's not great. And unfortunately, this payload was not compliant with the competition rules. We were a little bit underweight, so we lost some points in the final competition for that.
All right, so for structures, the big thing that made structures difficult was that it was all student researched and developed. So we made all the body tubes and a lot of the like fin can section out of student research and developed parts, and that added a lot of complexity. The requirements were it needed to stay above 1.5 calibers of stability. So if you guys haven't done it already, you'll learn that that's like the distance between your center of gravity and your center of pressure, and it's measured in body tube diameters. So in this case, it needed to be, those two values need to be 9 inches apart to be compliant to the rules. It also needs to withstand the operating stresses. So like it's a rocket, it goes pretty fast. This one goes, I think it went about Mach 1. So nothing outrageous, but it was still has to be able to handle that. And it needs to be constructed of lightweight materials. That's so that we can use a smaller motor so that we don't have to spend as much money to do each test flight, because motors get really expensive at this scale. It's like $600 or $700 a flight. Some challenges that the structures team faced. It was all new build techniques, so they had some bumps in the road working with these composite materials. There was also some fin damage during some of the test flights that they had to repair. And yeah, just SRAD manufacturing is pretty difficult. So they had a multitude of hoops they had to jump through to make that happen. All right, and then for the recovery system, some of the requirements for the recovery system are it needs to be dual deployment. Does anyone here not know what dual deployment is? Okay, great. So dual deployment is when you deploy a drogue chute at apogee, which is like the highest point of the flight. And that's a tiny little parachute that just makes sure the rocket doesn't accelerate when it's coming down. And then when you reach a certain altitude, it deploys a big parachute. And that's so that the rocket doesn't drift as far away. Because if you deploy this giant parachute at 10,000 feet, you're going to be walking like 5 miles to go get your rocket. So that's one of the competition requirements. Also needs redundant electronics. So that means there's 2 fully independent electrical systems, so that if one of them fails, the other one will still get the chutes out. And that just increases reliability in the recovery system. You also need GPS tracking. So there's a tracker right there. It's called the Featherweight GPS. And that's so that you can find your rocket, because especially at IREC, you're not able to just immediately walk out to go get your rocket. You have to wait, like in our case, how long do you wait?
I think we waited like 5 hours from once the rocket got on the ground to actually go pick it up.
Yeah, and if you don't have GPS coordinates, it makes it really difficult to find the rocket. And also you want live telemetry during the flight. You get that from the Featherweight GPS and from the Telemega, so that's like a fancy altimeter that's super expensive and beams down telemetry data, so you know like if the parachutes have deployed, how fast the rocket's moving, and all that fun stuff. Oh yeah, and the last thing, the electronics need to be powered remotely, so you need to be sure that the electronics cannot be powered on until the rocket is on the rail and ready to launch. And that's just a safety concern, because you don't want to move it around once electronic can blow things up.
Question. The power is onboard battery, right?
Yes.
Are you talking about activation, right?
Yes.
Yeah, okay.
Yeah, I guess that's poor wording. Some challenges that the recovery system faced, limited space. They didn't have a very large volume for their electronics or their parachutes, so they had to kind of work around that, and that was determined by the structures team and what they could do with the body tubes. And then also at the competition, our main parachute came out at apogee, so that means that the rocket drifted further than it was supposed to, and that was just a challenge. Here's an image of the avionics bay. You can see where the straddle logger, this screw switch is how you turn on the electronics, and then also the GPS module. And on right there, that's what the main parachute looks like.
For our propulsion system, we were initially wanting to do an SRAD motor. That's where you make your own motor, pour it, test it, do all that fun stuff. But unfortunately, we had a mishap during testing that forced us to switch over to a COTS motor. Those requirements were to bring the rocket to above 10,000 feet. Because we have an active control system, we want some margin for the active control system to actually do its job. So we have to be simmed to go above 10,000 feet, or in our case, whatever our target altitude was. We are using a COTS motor, and we need a thrust-to-weight ratio of greater than 5.
Now, thrust-to-weight ratio helps a lot with the control system because it makes sure that the rocket goes up straight, because all the equations we're using assume that the rocket is going relatively straight up.
Some of the challenges that this sub-team faced was obviously that testing mishap that forced us to switch to a COTS motor, and then also motor availability. One of the big appeals of a COTS motor is that you can build them, you can make them and build them for far cheaper than buying them. As Quentin already mentioned, they are around $500 to $600 each, and if you're buying them, that also severely limits the number of test flights you can do. And obviously you want as many test flights as
There's
possible.
also a shortage right now because military contracts exist and companies like those more than the hobby. Does anyone have any questions about what we've talked about so far? Quick questions.
What motor do you guys use?
We use an M2400. All right. Now we're going to deep dive into the control system. This is kind of where we worked on the rocket, so we're going to be more knowledgeable about this part of everything. So we'll start with the electrical system. Requirements for the electrical system. We need to be able to detect launch. So we have this custom flight computer that will do that for us. We need to know what altitude we're at. So we have this altimeter that will tell us what altitude we're at. We're going to be able to log and process data. That also happens on the custom flight computer. And we also need to be able to transmit telemetry. So we have this telemetry radio on board that will transmit telemetry. And then also we need control actuators. So we did that with this extra microcontroller. So the way that all of these, and one more thing. Some of the features on the custom flight computer, it had a big sensor suite. We had an IMU that has accelerometers and gyroscopes, an accelerometer for acceleration, barometer for measuring altitude, an SD card to store flight data, and it's also running on this TNC 4.0 microcontroller, which runs really fast, which is great for the amount of math that we need to be doing. So the way these all kind of work together is the extra microcontroller down there that it's called an Adafruit QT Py. They all communicate with each other over a serial connection. So the QT Py controls the motor and then tells the other flight computer where everything is at. The straddle logger is there because when you're competing, you get scored based on what a commercial altimeter reports as your final altitude. So one of the big things we did that's different from other teams is we pulled data direct from the competition altimeter and used that for all of our math and apogee prediction and all of that, and that helped tremendously in terms of getting a good score, because like sometimes they can be off by upwards of like 200 feet between like your altimeter versus the commercial. Here's what it looks like when it was all integrated. It doesn't look like that anymore, but it once did, and this is what the custom flight computer looks like.
So next up, talking about the software. Some of the requirements for the software was that it needed to be able to control the air brakes and record our data. Record our data both so we know what happened in flight and during our test flight so we can improve the system overall. We use Arduino C++ for the actual programming, and we use Git for version control. On the image right over there is a little snippet of the code base, and it is the active control section. So these like 20-ish lines are everything that actually controls the air brakes minus all the math that we do to get there. The top little portion is orientation of orbit. So if the rocket tips over more than 60 degrees in any direction, we don't really want to be doing anything at that point. So we close the air brakes and hope the chutes deploy and nothing breaks catastrophically. The middle section is the actual control. It uses an integral controller. We'll talk about that in a minute. And then we just set the air brake angle to that. And then if we're not doing any of those two things, we're in some other condition, and so we're just going to close the air brakes. That happens during descent or like while we're on the pads. We're not actively controlling the air brakes when the rocket's not moving. In our code, we use a loop setup to actually do a bunch of things, and this is what we do in the loop. First up is gathering data. This is highly dependent on what flight mode we're actually in. When we're actually flying the rocket, we are in a production mode. But if we're doing on-the-ground testing, we might be in a flight replay mode or in a Simulink sim. We'll talk about that in a minute. That's why there's that little asterisk next to pole sensors, because if we're in those two other flight modes that are not production, we don't actually need to get data from the sensors because we're not actually flying. We estimate our apogee, we track our orientation, we do some other orientation math. We handle state change as necessary. We'll talk about that in the next slide, I believe. And then we do any of the other extra stuff. So that's logging data, sending down telemetry, and doing state indication. On our board, there's a buzzer and an LED, both of which are used to tell us humans on the ground what state the board is in, which allows us to make sure it's safe. So for example, if it's in flight, it will be beeping a specific sequence and the LED will be magenta, versus if it's on the ground waiting to launch, it'll be green with a different, the LED will be green with a different beep sequence. So the graph right here is what we call the time since last log. So this is the cycle time of our loop. The minimum we saw in flight was about 18 milliseconds, the mean was 27, and the max was 206. You can see on some of these spikes right here. Those are likely due to data logging. These didn't actually impact our flight that much, which is why we didn't really investigate them or go around to minimize them, because 27 milliseconds is plenty fast for the math that we're doing and the frequency at which we need to be doing it. Moving into state change, our first state is boot up. It's what we do at the very beginning when the flight computer turns on and begins its life. It sets everything up, and we do that in this setup state. Then we move into awaiting arming. This was added so that when the rocket is on the rail, it doesn't accidentally detect launch, which is what we saw in some of our test flights and other times using this board. So at this point, it's open for serial debugging. That means we can use that radio and send it commands and do some debugging stuff, or we can plug in a USB and do those same items. We also start logging here. We log for the entire duration that the flight computer is on, just so we don't miss any data. Moving into the next state, we have awaiting launch. So after somebody has manually sent a command over and armed the rocket, it is now ready to launch. It's trying to detect that. We're still doing data logging here, but after an acceleration or altitude threshold is met, we've detected that we've launched. So here we are also logging data until we detect burnout. This requires a time minimum, and it requires our acceleration to be lower than a threshold, or it defaults after a timeout. After this, when we're in unpowered ascent and our speed is less than 0.5 Mach, this is where we're actually controlling the air brakes. This is where we're doing all the fancy math, opening them, and trying to hit our target altitude. Once we reach our apogee, which is the highest point in flight, the computer detects that and moves into the descent state. Here we make sure we close the air brakes. This is detected at a time delay, and it makes sure that we don't accidentally get the air brakes tangled in the parachute or any of the other lines that are being thrown out. And then finally, last state is landed. This one isn't technically necessary for our application because we don't really do anything different between descent and landed. It's detected over an acceleration threshold, or excuse me, an altitude threshold, and it's when the rocket is on the ground.
All right. Now moving on to the hardware, which is right here. So it's easier to talk about. Requirements for this, the air brakes needed to deploy symmetrically. Can anyone here imagine why that might be a problem if they deployed not symmetrically? Yeah. So they pitch over, and that's not good. We have experience with that here at Embry-Riddle, unfortunately. They also need to fail into a safe state. So the reason we have these brakes that come out like this is so that if something mechanically fails, they will force themselves shut. They won't stay stuck open and potentially cause that.
Question, is it air loads that'll force them shut, or?
Yeah. There's like, I'll talk about it in a second, but we did the simulations and found that like the brakes will experience upwards of like 80 pounds of force just from drag. So it's quite a bit. And also the rocket needs to stay stable. So like when the brakes open, you don't want the rocket to go unstable because you're moving your CP, and that's bad. And so revision 1 here on the top, we originally were using a stepper motor, which is really good for like knowing what the position of the brakes are and moving it super precisely. But we learned that the stepper motors aren't actually very strong, and 80 pounds is more than we were expecting. So we switched to a DC motor, which is what it is on now, and it's like much stronger, and we'll talk about that in a second. Challenges with the hardware: strength, it wasn't strong enough, and also position feedback. The stepper motor, you can kind of know where it is, but with a DC motor, you have no way of knowing where it is unless you have an additional sensor to tell you. Does anyone have any questions about what we just talked about?
Can you pass it?
Yeah, go ahead. All right.
What took the longest for the hardware side of things?
Developing the hardware?
Yeah.
That's a good question.
Moving to the DC motor.
Yeah, well, yeah, moving to the DC motor was rough because we found out that the stepper wasn't strong enough like a week before the competition. So,
And then had to find a DC motor.
yeah, which turns out we
Shout out to our first robotics team.
borrowed this from our first robotics team. So, yeah,
What testing did you do to figure out the loads were too high?
we will talk about that in just a second. All right.
Hell yeah.
Where'd the inspiration for the design come from?
I think it was like we did some research and looked at what other teams did, and also it's like kind of like how an umbrella opens. So one central actuator is better than having 4 because if one of the 4 fails, then you're asymmetric and it can pitch over, and that's bad. So, anyways, gonna go into the control logic now. Buckle up because this is where things get kind of intense. This is our control loop is. First, we estimate what the apogee is going to be. So this is happening after the motor's burned out. We're coasting through the air. It's a lot easier to do physics when there's not external acceleration in the form of like a motor. So we wait until that's done and it's coasting through the air. Estimate what we think the apogee is going to be because we want that to be 10,000 feet. So we need like a reference point. We subtract the target from that and that gives us an error. So like if we're expecting we're going to go to 10,500 feet, we subtract 10,000, then our error is 500, so it's positive, and we want to move the brakes in a positive direction to counteract that, right? That error goes into what is called an integral controller. Does anyone here know what a PID controller is?
Sick.
Okay, so this is like a PID controller without the P or the D term. It is just an integral. For anyone here who doesn't know what that is, the integral takes the error and it builds it up over time. So like if you have a bunch of positive error and you're moving your actuator and the error is not going away, it'll move the actuator more to try and make it go away. So that's how our control logic works. It's pretty simple in this application. Okay, now, how do we estimate our apogee? This turned out to be like one of the most difficult problems to solve because it's like there's a lot going on with the rocket and you don't want to try and make too many assumptions because there's so many, you want it to work in different conditions. So we used this equation to estimate our apogee, and I'm going to go through how we got each piece of this equation so that we could do the math properly. So this is apogee. That's labeled incorrectly.
This is the final altitude.
Yeah. So that's apogee. That's the final altitude. So it's the you take the current altitude and add it to the rest of that, and it'll give you your expected apogee. Burnout mass, this is what we can calculate this on the ground before the rocket flies, so that's just a constant. Current altitude, we collect this from the stratologger. So this is the commercial altimeter. This is where we are relying on the commercial altimeter instead of our altimeter, and what makes it so that we can get a more accurate scoring. Because it does not matter how close you actually are physically to 10,000 feet. Your altimeter just needs to think that you're at 10,000 feet, because that's how they score it. This is gravity, everyone's favorite constant. Oh, by the way, we're in the metric system because it's better than the imperial system.
Don't mix your units.
Yeah, don't do that.
We had a lot of problems with that.
That's bad. Burnout velocity. So the way we get this is we take our altitude from our barometer and the altitude from the stratologger. We take the derivative of both of those, and it gives us the slope, which is the velocity, and then we filter them together to give us our velocity. So that also proved to be pretty difficult, but we were able to test it offline, so it was good. Okay. Then there's also this K value, which has its own equation. This is rho, it's air density. We're able to calculate this using temperature, which is a constant. We assume it to be a constant, it's not actually a constant. And also pressure that we get from our barometer. This is the cross-sectional area. We're able to estimate this using CAD, and it's like a function based on how open the brakes are. So there's more math there. It's a lot of math. And then drag coefficient. This is another big difference we made. Originally, we thought we would need to calculate our drag coefficient beforehand using like a simulation tool like CFD or like OpenRocket or something to know what your drag coefficient is going to be of the rocket. And then we realized that the drag equation uses drag force, and we have all this information. So we're able to actively calculate what our current drag coefficient is during the flight. So this is the equation for drag coefficient. This P subscript D stands for dynamic pressure, which we calculate actively. This is the drag force. And again, this is the frontal area. It's the same value as before. We could probably simplify these equations, but we haven't.
Almost certainly.
We haven't done that yet. But we pre-calculate it the same way we do the other stuff. All right, so now this is dynamic pressure. It's 1/2 rho v squared. So those look like familiar variables, right? And they are the same variables as before. So we calculate the density the same way, and we calculate the velocity the same way. And this is the drag force. We get the burnout mass, which is still a constant, and the acceleration, which we're able to pull from our accelerometers. So that is what drives what our drag coefficient is data from the accelerometer, and it reads what the drag is on the vehicle. Any questions about any of that? Great. That's the only math in here, don't worry. I know some people hate math.
Moving into our first test flight, this happened, unfortunately, without all of our active control going, but we did get a chance to test the apogee estimation equations that Quentin just explained. For this flight, we had a couple different objectives. The first one was to gather data for us, our controls team. We flew with no air brakes open, and that allowed us to get a baseline of how the rocket performs throughout flight without our air brakes turned on. This proved to be very useful later on before our next test flight and then for our competition flight. We also were able to test payload video downlink and proved that structures was good to go. We had only minor damage, and they were able to fix it fairly easily. We also recovered successfully, which is really awesome. We got our rocket back and didn't plunge it into the earth and have to start from fresh. Super awesome. Successes, full recovery, amazing. We also successfully collected data. Controls did our job, we got those data. We got that data. Unfortunately, we did cone pretty hard. That occurs in flight when
It does weird aerodynamic stuff that I'm not qualified enough to talk about.
we moved around
Yeah, it's pitch,
in
roll,
not
cover.
great ways.
Just like
Yeah.
just that.
Did you get the good road deployment before the main with this one?
Yes. Everything worked as expected on this one.
And as said, we had some slight structural damage, but the structures team was able to fix that.
All right. Any questions about the control logic? Sweet. Flight simulation. This is also very important because motors are $700. You can't really rely on doing like 30 test flights or you're going to be out of money.
I wish we had money for 30 test flights.
Yeah, that'd be great. So one of the most useful simulation tools we use is called OpenRocket. Like I said before, it's the most commonly used program for subsonic rockets and will be, if any of you guys here are doing is everyone here doing like their level 1 with the hobby rockets? If you're not, you should. They're giving free kits away. That's great.
Yeah.
So if you learn how to build a rocket, you'll be using OpenRocket. It just simulates the flight, tells you what the altitude is going to be. You can move around the CG and stuff, and it's like really useful for learning about rockets. We used it in IREC for performance verification to make sure that we knew the rocket was going to go above our target altitude, so we actually had some room to work with, and we could bleed off the altitude and reach the target.
The next flight simulation ability that we had are what we call flight replays. So on test flight 1, we were able to collect data. We can just feed that right back into the flight computer and make it think it's flying. The control system won't actually be able to impact the numbers because we're just stepping through a file of numbers, but we can test other things such as logic in the code and making sure that it's actually like doing its job. In other rocketry projects we've done, there have been simple like coding set issues where, oh, it doesn't add commas in your data file, and then all that data is garbage. Flight replays are able to catch those types of issues. Uses real-life physics, yep. Can capture issues, and it only requires flying once. As soon as we have that data file, we can replay that file as many times as we want for literally the only cost of electricity. And on the picture right here, you can see one example. So on the top is data we collected from the Stratologger, which is that commercial altimeter in flight. And as you'll notice, it's very noisy. It goes from the actual altitude down to like between 0 and 100 really frequently. And that data is practically useless to us on the ground or in flight. But because we had flight replays, we were able to test different filtering options, and we're able to get it down to the graph you see at the bottom, which is phenomenal. Disadvantages, as I said, it can't actually simulate the changes that the control system is doing on the data because it's just stepping through. So it can't actually simulate the air brakes doing anything. And it also results in, what do you mean on this one? What do you mean on this?
Oh yeah, it only applies to like one set of data. So if there's like something weird with the data you collected, it could cause issues when you fly the rocket and get different data. This is a graph of our apogee estimation after doing a bunch of flight replays. Didn't we do like 200 flight replays?
At least.
Yeah, which is very expensive if we bought 200 motors. But I don't know what color it is, but like the spiky graph.
The green line that's spiking around the solid blue line is the apogee estimation, and then the one that comes up that also appears to be green, this is a terrible graph, is our altitude. So you can see as we approach our apogee, the apogee estimation gets better and better, and it's basically practically on that line.
And that solid line on the top is what the actual apogee was for the flight. So you can see we got it to be pretty reliable in that regard. All right, next simulation method, Simulink. Has anybody here used Simulink?
Yeah.
Has anybody here used MATLAB?
Yeah.
Okay, so all of you here who have used MATLAB, Simulink is like MATLAB, but it's like you get a bunch of blocks and they each execute MATLAB code and it goes in like a block diagram and it's really useful for simulating stuff. So that's what we used here. The difference with this simulation method is we're actually able to simulate what the air brakes do. So they can actually affect the flight and we can see the results of that, and we don't get that in a flight replay. Disadvantages. There is not realistic levels of sensor noise. So the simulation assumes that everything's like fine and perfect because the world is never perfect. It's actually got a lot more noise when you do real flights. But this was like, for example, your altitude is just like a perfect curve. But you can do all the air brake math and stuff with it, and it's great. So this is how the Simulink model works. It is, in this case, it's called software in the loop or hardware in the loop testing. So it's where you have your actual flight computer in the loop that you're simulating. So very similar to a flight replay, the way this works is it takes the Simulink simulation. So the way that starts is you give it a set of initial conditions. This simulation only simulates the coasting period of the flight because we wanted to simplify it and we don't want to have to worry about dealing with the acceleration of the motor and all of that because it could cause us to get bad data. The only part we care about is when it's coasting. So you give it a set of initial conditions that you can get from a real flight or from an open rocket flight. And it's like, at this point in the flight, this is what we expect all the velocities and positions to be on the rocket. You input that into the simulation runs, and it's just a physics model, so it just runs like carrying up to apogee, and outputs all of the position data. I think we take, so we do the control gains, and then also take state information like the position and the velocity of the rocket out of the Simulink model into the flight computer. And so again, the flight computer thinks that it's flying, does all of the math as it would in a real competition flight, and tries to move the air brakes. And so it does all the math, generates an air brake angle. That air brake angle goes back into the Simulink model on the other side, and the model simulates what the air brakes actually do to the flight. Does that make sense to everybody? Any questions about that? Great. So this is super useful, and it was especially useful even later when we were able to add an encoder to the motor, because it actually knows the exact position of the air brakes, how long they take to open, and like inconsistencies with that, and uses that for the simulation. And all of the communication here is done over serial. We also used the telemetry radio in this loop so that we could look at the data on the flight computer. So like the flight computer, we want to know where the flight computer thinks it is relative to the MATLAB simulation. All right. So drag modeling. How do we know how much drag the air brakes are going to produce? This proved to be a pretty difficult problem. The way that we chose to solve it is we have an if statement that takes the air brake angle that it's getting from the flight computer. If it's 0, then we use data from test flight 1 as the drag model. So we have like a curve fit so that it knows what the drag was during an actual test flight and uses that for all the physics. And then as soon as the brakes open, it uses a lookup table that we generated that changes the drag based on what we expect the air brakes, their performance to be. The reason that's super useful to have it separated like that is because we can put this gain on the lookup table, and we can change how effective the brakes are. So whatever model you use to simulate how effective your air brakes are going to be, it will never be perfect. That's just how it is. Like even if you do CFD and spend hours on it, it's never going to match what real life is. So you need a control system that can handle those differences, and we're able to simulate those differences so we can have a control system that handles those differences. Does that make sense to everybody? Perfect. Yeah, so generating the lookup table.
Yeah, so to generate the lookup table, we initially wanted to use CFD. Unfortunately, because we are engineering students here at Riddle, we procrastinated and ran out of some time. CFD takes a really long time. It can produce really great data, but it's also fairly slow. And we only needed a rough approximation of what our CD would be at to make this very fun 3D lookup table. So I had the privilege of running over 100 plus open rocket simulations in a car while we were driving to test flight 2 to generate this 3D lookup table. That was able to be plugged into the CFD model, or excuse me, the Simulink model, and was used in the event that the air brake model was not, or excuse me, the air brakes were not 0.
And just so you guys are aware, the inputs to this, does everyone here know how a lookup table works? It's just like, it's an array of data. So you give it a coordinate point, and it grabs data from that coordinate point. Does that make sense? So in this case, the coordinates and then that data, the slope there is what the actual data is. So the inputs to the lookup table are air brake angle and dynamic pressure, which we calculated previously, as we showed. It's a relationship between velocity and air density. So we can handle both of those things at the same time instead of needing to do them separately.
All right, so Simulink. is super amazing, and this is one of the example flights that we ran. As you can see on the left-hand graph, this is our air brake angle for the simulated flight. And on the right-hand side, you can see how it affects our actual apogee. So this blue line that's on the top here, it's a little spiky at the beginning and then calms down, is our estimated apogee. And as we open up the flight, or excuse me, as we open up the air brakes, this apogee estimation drops down significantly, and then we get closer and closer to our apogee until we are basically on it. For this test flight, we were 2 feet from our target, and that's pretty amazing, even though we're using simulated data at this point. This brings us into our other flight test. So for test flight 2, we had some other objectives. We wanted to gather more data for controls, and we wanted to give controls an opportunity to test the air brakes in flight. Here is a video of it. This was at LDRS in Fresno, California.
It's gonna be really hard to see.
Cody, heads up and let's watch it. Cody, heads up. 5, 8, 7.
There's a rocket there, I promise.
5, 4, 3, 2, 1.
All right. So the results for this flight were a little bit for the controls team. We opened up our air brakes late, so that meant that they didn't really impact flight as much. And also we proved that the stepper motor was deemed ineffective. We saw it try to open and fail to open because it was not able to open with all the forces that were on it. As Quentin explained, we did the math after this flight and figured out that the stepper motor was not powerful enough to open under actual flight conditions, which brings us into needing to change the actuator.
So, the way that we found out how much force the air brakes needed to handle is, I think this was a question earlier, is we ran Simulink simulations where like the brakes are actually opening and had one of the outputs on the flight computer calculate what the drag force is because we have all that information. And then we plotted it and saw what the maximum drag force was under varying conditions of drag, and that was roughly about 80 pounds. So we knew that they needed to handle at least 80 pounds. So to humor that, we were like, yeah, we're gonna test the stepper motor. Again, this is like a week before the competition. So we get the air brakes, we set them up on our kitchen table, put like...
We take a bucket,
Yeah, we
like
put
an
a-
upside down sand bucket, put it on top so it's hitting all 4 air brakes, and then we take like a 5-pound like dumbbell and put it on top and try to move the air brakes. And they immediately snapped closed. They did not work, could not move even 5 pounds, which was really fun to find out at this point in the timeline. But we progressed.
Yeah, so we had to switch to a DC motor. So the difference between a DC motor and a stepper motor, the DC motor has no idea where it is. It just moves. So we needed to add an encoder, which records the position of the motor. Again, we stole the encoder, borrowed the encoder from our robotics team, and used that for the DC motor. And then the DC motor had its own PID controller to control the air brake position. So anyone here who's used PID controllers in robotics, it's the same idea and it's even the same hardware. And this had significantly more torque. We calculated it, it has like 200 pounds of torque at least. Or not torque, but like we can can handle 200 pounds of drag on it. So, and we could have true hardware in the loop. We're actually getting feedback from the encoder during the simulations instead of just assuming that the stepper motor is where we tell it to go. And here's a video of them opening.
They can also open and close much faster, which was an issue with the stepper motor as well.
Oh yeah, and the lead screw. We originally the stepper motor we had a lead screw like built into it. This one didn't, so I had to steal it from my 3D printer, and it just like lopped off the end of it and used it for this.
You had a little hardware problem too, didn't you?
Yes, the encoder. We like heavily modified the encoder. We cut the encoder in half, drilled a hole in it, and glued something to like the spinning part because it was too big to use like the real thing.
Team doesn't do this, it's fine.
And then the night before the competition flight, that part that we glued in broke. So we had to like try and fix it, and that was the source of our lack of sleep on the competition flight,
One of the sources.
which we're going to talk about now.
Yeah, so competition flight. Changes we made for this competition flight before the other one. The biggest one is that we changed our target altitude. We did, in the many long nights before the competition, we did a bunch of sims. We were trying to refine we were trying to tune our control system a little bit better, and we were running into a problem of just not reaching enough altitude. So the decision was made to lower our target altitude down from 10,000 feet to 9,800 feet. That does technically lose us some points in the main category, but unfortunately we had already missed a ton of points, so we were mainly focusing on the Barrowman Award, which I at least am really glad we did. We finally selected our control algorithm. We had that new actuator in there, and we tuned the control system, as I said. So this is one of the examples of some of the flight data we got from the flight. As you can see right here, our air brakes actually start opening. That is after the Mach threshold was engaged. And you can see there's a little bit of jitteriness immediately afterwards in both our apogee estimation and our, maybe a little bit more than a little bit, and our like target air brake angle, and that is due to barometric noise inside the rocket.
The problem was we didn't have the compartment between the sensors and the area where the air brakes open sealed off properly. So as soon as they opened, a bunch of air did air things and made it get really confused. But it's fine because we were still able to use the air brakes, and if you look at this graph, it goes from
This is zoomed into the apogee estimation and altitude graph that you saw before on the top left.
this is apogee estimation, right? Yep. Yeah, so this yellow one is apogee estimation, and typically it's like a straight line. Because the brakes were moving, it was also moving, and brought us from down here, I think this is 200 feet away from the target, which where it would have stayed if the brakes weren't doing anything, and brought it all the way up here to 44 feet away from the target. So that's verification that the air brakes actually worked.
So this graph actually shows an altitude difference of about 55 feet. We had two competition altimeters on this on this rocket, and the one that Controls was using was 55 feet off. The recovery altimeter, though, was 44 feet off, and because it was also a competition altimeter, we were able to just choose which altimeter we want to use for scoring, and obviously we chose the one that is closer. This also just goes to highlight how different altimeters, even two of the exact same product made by the exact same company and on the same rocket, can have different altitude readings.
And we even our barometer, I'm fairly certain our barometer was
We were 150
to 100
yeah.
feet away from what the stratologger gave us. All right, lessons learned. We learned a lot of them. So that's at the competition. The biggest lesson that we learned is debugging takes a really long time. If anyone here has worked with any sort of electrical or software system, you know exactly what I'm talking about. So do you want to talk about our stepper motor implementation?
Yeah, so I don't know, has anybody here programmed a stepper motor controller before without the use of a control board? Cool, I'll save you the time. Don't. It's not very fun. It's so annoying. You have to manually flip a pin back and forth to make it step. And that not only is really annoying to program because it is blocking, that means you're not allowed to do anything else in the code while you're flipping this pin back and forth a bunch of times. You also have to flip it back and forth a lot of times. For the full range, I believe we were looking at about 26,000 steps, which means the code has to flip back and forth 26,000 times, and there's a time delay in there. We need about 100 nanoseconds in between each flip back and forth, which if you're doing 26,000 times, really adds up. Also, it's blocking, it's slow, and it doesn't work. A lot more time than you need. So when we were initially doing the stepper motor implementation for this, we found a library, we implemented that, and we were testing it, and I was like, great, hunky-dory, this is all working great. And then I realized it was blocking, which means we totally can't use it, and I had to go back to square one. That was a really big, unexpected problem, and leads me into one of my favorite sayings, which is, in debugging, you can be 1 hour away from solving your problem for 24 hours in a row. Always a lot more time than you think you're going to need for debugging, because it's really easy to fall into that trap of oh, I'm so close, I just need to keep working. Also, one of the really big lessons we learned is that Simulink and hardware loop data testing is so overpowered. We were able to, in the course of the entire competition, simulate upwards of 300 flights. And that was totally not possible if we were relying on just pure actual test flights. We barely were able to afford 2 test flights, never mind 300. I wish we were made of infinite money, but unfortunately
And if you go to the competition, most of the teams, like a good percentage of the teams there, have air brakes, and they just don't fly them because they couldn't get enough test flights. But we got 300 test flights.
Yeah,
So-
got over 300. I opened up the SD card. We just had like 300 plus sims. It was amazing. So that brings us into what's next. IREC 2026 is heavily recruiting right now. All of you are invited to join. We're having our first meeting today, library room 218 at 7:30. We need people for all of the subsystems. We need structures, payload recovery controls, and media. We're not requiring you to already have experience. So if you're interested and want to learn, please join us at the library room at 7:30. That'd be real great. And also, the IREC competition is a little bit more than engineering. There is obviously the engineering, the actual rocket, and all that stuff, but there's also a video competition and the documentation package, which is a real shame that we keep missing. So I'm going to be pushing that we meet those deadlines really hard, because I think we have a really, really, really good shot at actually winning IREC, or at least placing in the top 5, if we can do those things. The contact information for me and Quentin is right here on the side. And we're happy to answer any questions you have about the whole project overall right now.
We also forgot to mention, but we placed 4th place for the Berriman Award out of 180 teams, and we didn't get a single test flight with the brakes actually opening. So we're anticipating some pretty high levels of success this year. Any questions at all about the project?
Would you be going for the SRAD category this year?
Probably not. It still hasn't been decided.
Yeah.
How does your system of air brakes and all the things behind that, how can that be applied to other rockets using different geometries and different air brake styles?
Want me to take this?
Yeah.
Okay, so because we are calculating the coefficient of drag on the fly, it does not matter what the shape of your rocket is at all. Once you have tuned values for the set of air brakes, so like this set of air brakes can go into any 6-inch rocket and they will work just the same with the same tuning values every time, because we're calculating the coefficient of drag on the fly. So like if you make a different geometry, same story, you just have to like do the Simulink stuff and find the tuned values, and then it will work on any rocket of that size. So like if you make a 3-inch one, you put it in any 3-inch rocket and it'll do the same thing.
So you just need one test flight then?
Yeah, you get one test flight to get a flight profile, and then you use the Simulink model and get your control gains, and you're good.
What other methods of altitude control have been tested or are out there?
So I actually learned very recently about a team that is doing like a water ballast system. I'm not sure exactly how it's going to work, but they're like planning to release water and change their mass and use that to control their altitude.
You can also deploy the chute.
You could.
Aim for 30,000 feet, deploy it in 9,500.
It's an option.
Are you guys planning to use get the exact same data and do the exact same equation from last year, or is there be any change with that?
We are absolutely going to change the control logic. One of the biggest changes we're going to make is we're going to switch to a full PID controller, and I think that will help us a lot to handle the like variations in how effective the brakes are. Because this year we were only able to use an integral controller because we were controlling the position of the brakes. We're going to change the system so that we're now controlling the velocity of the brakes, and it should make a big difference.
Also of note, because we have the tools that we designed last semester, or for last year, that will also rapidly speed up our timeline for this semester. Other questions? Yeah.
So, what's your guys' timeline for this project? When's the next competition and stuff?
Next
Yeah.
competition is in June, but we want to get like the entire hardware stuff done by the end of this semester. So like get the rocket finished and ready to fly by the end of the semester.
What size rocket you're running with?
It doesn't we don't know
Come
yet.
to this meeting and we'll
Yeah,
decide
good.
that.
Up for debate. Probably small, because so then motors are cheaper. To spend $1,300 on a motor.
Other questions?
So are SRAD motors the norm for IREC, or do you default to like commercial motors?
SRAD motors are very popular. There were a lot of SRAD motors we saw at the competition.
COTS is way more popular. COTS is
Never
like,
mind.
the percentage of people using COTS is way higher than the percentage of people using SRAD. We haven't like fully locked into our decision of which category we're competing in yet, but we're leaning toward 10K COTS so that we can focus on documentation and getting a really good score.
Yeah, I just want to add that if you guys had turned in your documentation this time, you would have been.
Yeah, we would have been like top 10 if the documentation was done on time. Overall.
Is it prize money?
No, there might be.
Maybe.
I can't remember. There
Well,
might be
back to-
prize money. I think there is. For like the top 3 teams. And you get like major bragging rights.
Screw the money. All you get rather.
Any more questions?
So I'm also interested in height. But I don't wanna like overexert myself in like special things and things. So I'm already doing, or gonna be doing pocket rockets. And I'm interested in finding out more about height. Do you think like doing all 3 would be a problem, or?
It depends on how involved you want to be. If you like want to show up to IREC as more of like an educational thing where you just want to learn about stuff, then it won't be as much of a time commitment. But like if you want to really get your hands dirty and like put a lot of hours into hardware, then it'll be more of a time commitment. It's like really up to you. We really want to focus on teaching people this year, especially with the control system now that we have all our tools developed. Anybody else? Sweet.
Question. Everybody here knows about the academic requirements to work on this, right? You're all familiar with that? You might want to brief them on that at this meeting, okay? Because we don't want people signing up if they're not gonna be able to be on the team.
Yeah, we can do that.
Sweet. Thank you guys all for coming. We appreciate it. Hopefully we see some people at the meeting.
It's a note for myself, so you don't read it. Yeah. Any other questions? Cool. Thank you all for coming. If you're interested, 7:30.